lesson. All right, so your reminders, the Positive Physics Unit 15 on torque, that assessment's due tonight. Make sure you submit a screenshot that shows your name and the percentages. If you're still in the assessment, up in the top right-hand corner, there's a nice little summary there that you can just take a tiny little screenshot, or you can go to the dashboard and then it takes a bigger screenshot to get everything included. But make sure I can see your original score, your finalized corrected score, and your name somewhere, and then submit that on Axis. Unit 16 is due the night of our next class, so it's not due during class. We just keep that 11:59 for everything just so it's consistent. You have to remember different times. So just keep the same time, but the next time we have class, it'll be due that night. And that one is on angular momentum and rotational inertia, the other things that we've been talking about in addition to torque. So we've covered most of it. This is the last topic, angular momentum, that we need to cover. Any questions about timelines, deadlines, due dates? All right, let's jump right in then. So we're going to start with a little brain teaser. And I've been having a few of these little picture imagining things. So we're going to do another one today and have you make some predictions. So based on, not on angular momentum yet, we're going to learn that here in a few minutes, but based on rotational inertia, I've got these two objects. One is a cylinder, one is a hoop, and they have the same diameter. Okay. They also have roughly the same weight. All right, so if you want to kind of give us a student's approval, are they roughly the same weight?
Yes, I can confirm they're roughly the same weight.
Thank you, appreciate it. Because you never know, teachers can just, try to deceive you. So I want to make sure there's this, and I didn't pay you beforehand or anything. So it's an honest opinion. These are actually roughly the same weight.
Yes, yes.
All right, so the thing that I want you to predict is, okay, if I have these two on here, and hopefully the camera will be able to find me okay. If you're on Zoom, you may want to pin it so that you can see it more full screen. But I'm going to just let go of this disc and this hoop, and we're going to see which one's going to win the race. But I want you to place your bets, not financially, but mentally. So what do you think? Which one will win this race down the ramp? Will it be the solid disc or the hollow hoop? Solid disc. How many say disc? Raise your hand if you're in here.
I'm going to say that, yeah.
Okay. You think something different, Jack, or just not committing? Oh, you had, okay. Yeah. How about you guys in the Zoom? Disc or hoop?
Disc.
Disc.
Everybody says disc. Nobody says hoop.
It's got that air friction.
Okay. All right. So who can give me, someone in the Zoom, who can give me a good scientific reason why you're picking disc?
I was thinking that because more of the mass is towards the center, it would be easier to turn.
Okay, good. More of the mass is towards the center, so it's easier to turn. How about you, Nat?
It's able to have like a drag because of how on the hoop, because of how the hoop shape, like the back when it's going down, air can catch against it, pulling it backwards.
That is true. But in this short run, that will probably make some slight difference that wouldn't affect it. Now, if it was a long run, then it will. But even in the short run, there's going to be a clear winner. Yeah, Ethan?
The disc has an inertia of like 1/2 mr squared, and the hoop is mr squared. And so the disc is like half as easy to move, or twice as easy to move. And they have the same gravitational force on them.
Good. Since their masses are the same, gravity is going to affect them. They have the same weight. And 1/2 mr squared versus mr squared. And that's the one thing, I'm glad you guys caught on to it. We were torn first period. And this is often one of the things that makes it a struggle for students. It's like, oh, this has 1/2 mr squared. This has mr squared. So this was going to win. This only has half. Okay? But you have to remember what the mr squared is telling us, right? And not just that, yeah, the bigger number doesn't win in this case. All right. So if this is mr squared, what we're saying is how difficult is it to accelerate? The bigger the number, the harder it is to accelerate, right? So we want the smaller number, right? And so since this is half the inertia, it's easier to accelerate. This is twice the inertia, it's harder to accelerate. All right, so this is going to be it. You guys would all won money if I had money to give you.
Watch us all be wrong.
Physics suddenly changes. All right, so 3, 2, 1.
Let's go.
Good job, team.
You get a pass.
Easy.
All right, so you guys did a nice job of thinking that through. Just want to do that quickly. Like I said, it's not just first period. They did great, but they had a little confusion. Maybe they're a little sleepy, but every year there's a lot of students that just they right away think, oh, that's the bigger number, so it's going to be faster. And it's reverse of that. You have to stop and just pause long enough to recognize, oh, wait a minute. Inertia is the resistance to accelerate, not making it accelerate. And so you have to kind of make sure you lock that in. All right, very good. Well, today's lesson is on angular momentum. And this is one that also creates some really interesting scenarios. So, and I'll be demonstrating some things, but in this picture, a little bit today and more so in other days, we'll keep coming back and revisiting this. I still think this unit of rotation is the hardest unit of the year. And we're finishing it today. But if you stop and think about the dozens of equations we've added and the dozens of new variables we've added and all the new concepts, and a lot of them are pretty intuitive, but some of them are not. And just keeping straight, what is an I, what is an L, what are all these things? There's just a lot to absorb. So we will continue to keep coming back, and I'll keep bringing different brain teasers and doing different demonstrations to make you revisit it over and over these next 2 months, because I do think it's always on the exam in multiple forms. And 2, I think it is the hardest one to really sink into your deep understanding, although you guys really impressed me with that one. So maybe you won't need as much review. So you can see a picture here of a ballet dancer, it looks like. And then we've also, this would apply for a skater, also for divers. So if you've ever seen how skaters, when they're skating and they have their arms outstretched and they're spinning, and then as they bring their arms and they spin faster and faster and faster, we're going to see today why that happens. We're going to prove today mathematically why that happens based on the physics. It works for ballet dancers as well. So as they're spinning, when they have their arms out, then they'll bring them over their head and they're centering their mass, right? Divers the same way. If they're in a flat out position flipping, it's slower. And then if they go into a pike position, it's faster. And if they go into a curl or tucked position, it's even faster, right? So they're centraling their mass. They're putting their mass more centrally located. And we're going to see, we kind of know that happens, but we're going to see what's the physics behind it, what's the math behind it, why does it happen? And it's based on this first bullet point, law of conservation of angular momentum. Then we're going to study something that's pretty trippy. Something that's moving in a straight line can have angular momentum, even though it's not moving in a rotational fashion. And it has to be a part of a system for that to be true, but we'll prove again why it's true. And we'll also talk about how you can solve problems with that concept. And then the third bullet point is something we will not cover. There are a few bits and pieces kind of spread throughout this textbook that are actually AP Physics 2 topics. Kepler's laws is one of those. So we're not going to spend time covering that. The way they handle AP Physics 2, this publisher, is they say, well, you've already taken AP 1, so you've already got the book, and it's got some stuff in there for you already. And then the next one is just like a supplement. It's not a full second textbook, although it's almost as big. So it probably costs almost as much too. I don't know, but I think it's like a marketing thing. Oh, you don't have to buy a supplement. You don't have to buy a whole new textbook. It's as big and as expensive, but
It's just big and costs the same amount.
But anyway, so this is one of those topics where they've snuck in some AP2 stuff. It is related to what we're talking about here, but it's not something you need to know for the exam. So we're not going to spend the mental energy to try to learn it or take the time. So that third bullet point, we're just going to cut off the list. All right, so let's talk about what is angular momentum. So briefly, before we break this down, momentum just in general is a term that I'm sure you're fairly familiar with. If I said, hey, Jack, can you use momentum in a sentence?
Yeah, I can.
Okay, and it would even make sense probably, right? I mean, not just
Probably.
momentum is a word. There you go. No, I'm sure all of you could use momentum in a sentence and make it applicable. Like even in something like sports. Oh, that team has the momentum right now, right? They're winning and they have the momentum, or they're making a comeback and they have the momentum. Or we can talk about, oh, I was trying to stop, but I had too much momentum. Or that car was trying to stop, but it had too much momentum. Like we kind of know conceptually what we're talking about with that word, but what the concept of momentum is mathematically is it's factoring in the mass of the object and its velocity. Okay, and even more specifically than mass, it's factoring in its inertia. And for something moving in a straight line, that is the mass. But for something rotating, it's both the mass and how the mass is distributed, right? So momentum is the inertia that an object possesses and its velocity. Both of those things matter. If I wanted to stop two people running down a hill, and one of them was my 50-pound grandchild, and another one was like a 300-pound sumo wrestler, I'm going to pick my grandchild every time, not only because I love them, but because I don't want to get smashed by that 300-pound sumo wrestler, right? So we know that the inertia that they have matters, and so the mass that they have matters. Well, angular momentum is the same thing, but not, instead of something moving in a straight line with momentum, it's something that's rotating with momentum. Okay, so it is in rotation, it has movement. And because it has movement, it has momentum. And it's still the same principle. It factors in the inertia that it has rotationally, and it factors in the speed that it has rotationally. Well, rotational inertia is I. That's what we've been working on the last several lessons. And rotational speed or velocity is omega. That's what we've been working on for about 3 weeks now, right? So we are getting more and more familiar with these terms, but when we multiply the value of the inertia times the value of the velocity rotationally, we get a rotational momentum or an angular momentum. Why do we use letter L? No one seems to know. I don't know. I looked it up once and I couldn't find any good explanation of why they chose L. Sometimes I think they're just running out of letters, like just
they already used small m and big M. So
yeah, so
they've already used T in multiple different ways.
exactly.
And mu's already gone.
Yeah, so I think they just are running out. So let's just use L. And there's an L in the word angular, but for linear it's P. So I don't know where that comes from. Anyway, so they use L for angular momentum. We're going to see linear momentum here in a few slides. It's actually lowercase p. Now, angular momentum has the units kilograms times meters squared per second. And if you look at what we're using to find it, that makes sense because rotational inertia is based on some fraction mr squared. That fraction might be 1, but it's something mr squared. And so it's going to be kilogram meters squared. And then the velocity we already know is going to be radians squared or radians per second because we're talking about rotational velocity. So if we multiply kilograms times meters squared by radians per second, radians are unitless, so we just end up getting kilogram meters squared per second. So the units make sense if you remember what I and omega's units are. Nothing special about that. And it's actually a pretty easy formula to use. It's pretty simple, straightforward, only 3 variables, but one of them is new. So let's start with the simplest scenario. We have a tiny rotating object. So, and this rotating object is 4 kilograms. It's crazy because the other day we had something that had a diameter of 5 meters and was 4 kilograms. Now we got a tiny object, still 4 kilograms. I'm not sure where they get these numbers from. But it's rotating around an axis that is 2 meters in radius. And it's moving with an angular velocity of 30 radians per second. So this is clearly not to scale. But if we're going to use that momentum equation, angular momentum equation, we can figure out the I value and we're given the omega. How would we calculate the I value?
4 kilograms times 2 meters squared.
We take the mass times the radius squared. So the 4 kilograms times 2 meters squared. So I, for a tiny object or a hoop, is mr squared. And so we know the m, we know the r, we know the omega. We can plug in all those numbers. And the momentum that this little particle has is 480 kilogram meters squared per second.
That's pretty fast.
Now, that's a pretty big value, but all the mass is compacted into that tiny space. Okay. Questions? As in the Zoom, you okay? Questions?
Question.
Yeah.
What do you do with momentum? Like what is it useful for?
Stay tuned. Yeah. So in just a few minutes, we're going to apply it in several different ways and explain. There's one principle that sort of makes it extremely powerful.
All right.
All right.
The most powerful of the equation.
It is actually one of the most powerful concepts for problem solving.
That's cool.
Yeah. So in this scenario, we have still a 2 meter radius and still a 4 kilogram object, but now that mass is spread out over a disk instead of compacted into a small particle or small object. Still moving at 30 radians per second. So now that it's a disk, we still are going to use the same momentum equation, but how are we going to have to change this?
Divide by 2 because it's 1/2 mr squared instead of just mr squared.
Yeah, the disk is 1/2 mr squared for its I value. And if we know the mass is still 4 kilograms, and we know the radius is still 2 meters, and we got to square that, and we know that the velocity is still 30 radians per second, we should get half of what we got on the previous problem, because that's the only number that changed, is adding the half. So when we spread the mass out, it's actually easier to stop instead of having that mass all compacted into a small area. So it has less momentum when that mass is spread out.
That's like the concept of like seatbelts.
Mm-hmm. That's one of the big ones we're going to talk about in the next couple of weeks is seatbelts, airbags, all those kind of things. We're actually going to connect it to another concept called impulse. But yeah, that's exactly the right thought that you're thinking there. All right, so that is angular momentum. And right now it's basically just an equation to you, right? And maybe generally a concept of its inertia and velocity that the object possesses. But why is it important? How do we use it? And can we combine it? So one of the things we've been doing a lot recently is like with kinetic energy. Oh, it can have rotational kinetic energy and it can have translational. And we did that with a couple of things along in this unit, right? Well, let's think about the linear translational part and let's think about the rotational. We're going to do the same thing with momentum here. And the plural of momentum is momenta. So this object, if it's both spinning and moving in a translational manner, has two kinds of momentum. It will have the mass of 4 kilograms given here and the rotational inertia of 5 kilogram meters squared. So they're just giving you the I value rather than a formula. It's moving translationally at 3 meters per second and moving rotationally at 2 radians per second. So here's your next new equation. There's 3 new equations today. One we've already seen, L equals I omega. Here's your second one, P equals mv. And I'm not going to explain where P equals mv comes from yet because that's next week. But I'm just introducing it. Like I said, all these crossover events, explaining a little bit of what's coming along with what we're doing right now. So linear momentum clearly, obviously, uses the letter P for the variable, and it is still the inertia that the object possesses times its velocity. But when it's moving in a straight line, its inertia is just its mass, inertial mass. And when it's talking about velocity in a straight line, we use V because it would be meters per second, not radians per second. So hopefully you can see that these equations are very similar. We're solving for momentum in both cases. We're considering the inertia that the objects have and their velocities. But in one case, it's the rotational inertia and velocity, and the other, it's the linear inertia or inertial mass and linear velocity. Now, the tricky part is, if we plug these numbers in, we get 2 different answers. Okay, that's not too surprising. But we also get 2 different units. For linear momentum, we're going to get kilogram meters per second. For angular momentum, because of how we calculate I, taking into account how the mass is distributed, we end up getting kilogram meters squared per second. So if we wanted to know the total momentum for this triangle, if this triangle is both spinning and flying across the screen here, can we just add those 2 numbers together?
No.
No, they don't have the same unit. So this is not like we could do with energy. When we learned kinetic energy of rotation and kinetic energy in translation, 2 different formulas, but they ended up giving us a value with the same unit. So we could add those together and get the total kinetic energy. Can't do that with momentum, right? You actually just have to think about the linear momentum it possesses and the angular momentum it possesses separately because they are defined a bit differently in their units. So in conclusion, if you have something that has both linear and angular momentum, that's fine. You can find both, but you cannot add them together since their units are not alike. They would not be like terms. Questions? Yeah, Ethan?
I might be getting ahead, but could you say the units of linear momentum are like Newton seconds?
Yeah, I haven't really seen it written that way, but it's correct. Yeah.
And would that mean anything? Would that be like the force over time, the force times the time that you'd have to apply to it to stop it?
That might be important to know. And that's called impulse. That's coming up soon. Yeah. And actually, when we see Newton seconds, usually we use that to describe impulse.
Okay.
Because that more visually represents the formula.
Yeah.
And what we're going to prove later is that those two things are equal. And makes sense when you see their units are the same.
Yeah.
And so we're going to actually prove conceptually that not only are their units the same, their values are equal. But that's another week or two down the road. So yeah.
All right.
Good. Anything else? All right. Could you put the units of Newton seconds for momentum? Sure, you could. Normally you wouldn't see it that way, but if you wrote it, it wouldn't be wrong. All right, so here is a quick summary. We're going to fill in a couple blanks. We'll talk about it, fill in a couple blanks in the bottom right. You can see a couple question marks here. And then after that, I would suggest if you're in the Zoom that you screenshot it. It's a nice little summary. And if you're in here, once we've figured out what those question marks are, it might be a good thing to take a picture of. We're going to spend a lot of time talking about linear momentum starting next week. But today is the only day we're talking about angular momentum. And so if we kind of compare them, linear is P for the variable equals the inertia in mass times the velocity in meters per second. Angular momentum is L for the variable, I for the rotational inertia times omega for the angular velocity. Both kinds of momenta are conserved. Now, what we mean by that is what we see below that. So on the blue side, the linear momentum side, it says law of conservation of linear momentum. And this conservation law is what makes momentum in either form extremely powerful for solving problems because it's conserved. So what the law of conservation of linear momentum says is what we see below that. If there's no external force on the system, the linear momentum of the system is constant. That's what the law of conservation of linear momentum tells us. And it makes it incredibly powerful. We're going to go through 4 problems of angular momentum and show that it is also constant. But there's a couple slight changes we need to make in that definition. One of them should be pretty obvious. The other one may be a little less obvious, but I think you're going to be able to come up with it. So if we look at the law of conservation of angular momentum, if there is no net external, not force, but what's close to force, but rotation, yeah, torque. If there's no external torque on a system, then the angular, that was the easier one. The angular momentum of the system is constant, since we're defining conservation of angular momentum. But the torque is the one that, okay, yeah, force and torque are kind of hand in hand. They don't mean the same thing, but they're kind of corollaries in the 2 different realms of the linear versus the angular motion or rotational motion. So nice little summary there. We will today, from now on, focus almost entirely on the angular momentum. And then in weeks ahead, we will focus almost entirely on the linear momentum, right? But I wanted you to see them both. Start to introduce the linear one now, even though it's coming down the road very quickly. All right, so in this, oh, sure. Anybody else need a shot of it, screenshot or a picture? So let's break down angular momentum a little bit more, since that's the focus today. Here's our first example. And this is more conceptual than a problem to solve. But we've got 2 things we've been talking about. One we've been talking about for a few days, rotational inertia, I. And then this new thing, L, rotational or angular momentum. So I, the inertia that an object has, is based on its mass and the distribution of its mass, which we represent with R. Now, that object's mass won't likely change in most scenarios. It'll stay constant, even though it may be changing in its motion. Normally, its mass isn't changing simultaneously. So its mass is normally fixed. But if we change the radius, if we change the distribution of that mass, that's going to affect the I value. So as the R gets smaller, the I has to also get smaller. And that's what we've been talking about with if the mass is more centrally located, like the disc and the hoop that we did our little race with at the beginning of class. The mass was more centrally located in the disc, so it had less I. Since it had less I inertia, it was easier to accelerate down the ramp. Now, L, we just said, and they've restated it here at the bottom in red, if there's no net external torque, the angular momentum is constant. That's the law of conservation of angular momentum. So if there's no external torque, if we're not adding any other thing to the system here, then that L value has to stay the same. And if we look at this barbell setup here we have in the picture, the weights are clear out on the edge. So high momentum, or sorry, high inertia or low inertia? Rotationally.
High inertia.
High rotational inertia. Now, linearly, if I carry that barbell, that dumbbell across the room, whether the weights are on the edges or whether they're in the middle, doesn't matter if I'm just carrying it straight across the room. But rotationally, it's harder when they're out on the edge, right? The I value is big. But if those weights move to the center, what happens to the R value? It decreases. So then what happens to the I value?
It decreases.
It decreases. And if the L can't change and L equals I times omega, if the L is constant, as the I gets smaller, the omega has to get bigger, right? Like if the I is 20 and the omega is 1, if the I becomes 10, the omega has to be 2. If the I becomes 5, the omega has to be 4. If the I becomes 2, the omega has to be 10. As one goes down, the other has to go up to keep getting the same constant answer, right? So they're just going to simulate that with this animation. As the weights slide towards the middle, it's going to visually speed up. And in the formula, you're going to see the I font get smaller and the omega font get bigger. So trying to show you visually both ways that that velocity is going to increase because the I value is decreasing. That's how skaters can speed up by pulling their arms in. That's how divers can speed up by going to a tuck position. Okay, they're getting their mass more centrally located, which makes their radius decrease, which makes their I value decrease, which makes their omega increase. Because if they're in the air flying on a dive, yeah, there may be some air resistance, but it's probably fairly negligible. There's no external torque changing them. So whatever momentum they have when they leave the diving board, the amount of momentum is fixed. The only thing they can change is either their I value by scrunching up or spreading out. And whichever way they do, that's going to also change their velocity of rotation. Yeah, Ethan?
How come then? So when you tuck, that requires energy. You have to like pull yourself in. So how come one way changing the equation requires energy and the other way it like takes less energy?
What do you mean by other way? I'm not sure I follow.
So if I make my I value smaller, and my omega bigger, that takes energy to pull in. But if I make my I value bigger and spread out, that takes like less energy, or it takes energy out of my body, I guess. Because you have to increase the centripetal force to tuck, and then you decrease it to untuck.
Oh, you're talking about centripetal?
I guess because you need it to pull the mass in.
Yeah, so you're applying force in your muscles to pull the mass in.
Okay.
Is that what you're saying?
Yeah.
Okay.
And then you apply force outward, not really outward, but you like.
Yeah, you're applying a force to push the mass back out.
Is it? I feel like it's just like because not centrifugal force, but the inertia just pulls it out on its own. Like if you had,
I see what you're saying.
Frictionless dumbbell.
I see. Okay, now I'm tracking what you're saying. So to be able to pull your arms in, you're going against the inertia, and to be able to pull your arms out, it's going with the inertia.
Yeah.
So it would take less work, one way or another.
Yeah. And is there like something else that balances that keeps everything equal, or
for energy?
Yeah.
Well, there's energy stored in the system, and there's energy of motion, and there's rotational and translational energies. So the energy flow is going to be a bit different. And in fact, what we're going to find out is while momentum is always conserved, kinetic energy is not. And so, but that's also a future lesson coming in the next couple weeks. So energy as a whole is conserved, but kinetic energy is not. So that energy of motion of you moving your arms in and out, you can lose energy out of the system kinetically. But that's coming up soon. So I think that it took me a minute to connect what you're saying. Once I got tracking with you, I see what you're asking, and that's a good question. And it comes down to the energy not necessarily being conserved in kinetic.
Okay.
Yeah, good question. Anything else you want to ask about angular momentum? All right. So here is a problem. It was actually on the one of the FRQs a couple of years ago, 3 or 4 years ago, I think. And it was slightly different, but really the same scenario. We had one disk that's spinning in a certain direction. And I'm going to have to, yeah, because it's too much noise. And since we're recording, it'll be a little loud. We'll let you back in.
For the better.
Yeah, we'll let you back in. So we've got one disk that's spinning us one direction. So this blue disk on top is spinning counterclockwise. And then we've got this orange disk down below spinning clockwise. And it says over here on the top, on the right, the rotating top disk falls onto the rotating bottom disks and sticks to it. Find their final angular velocity. And this kind of problem is very frequently used in FRQs, whether they're spinning or moving in straight lines. They always seem to like dropping one thing onto the next and making them stick together. That's like a real frequent theme of things that happen in their questions. And so in this problem, they're saying, well, the blue cylinder, this disk, has an I value of 2 kilogram-meters squared, and it is moving 5 radians per second, and they're calling its counterclockwise direction positive for this problem. The orange disk down below only has an I value of 1 kilogram-meters squared. So even though it's bigger, it has less inertia. So the mass is distributed in a similar fashion, but it must have less mass because it's got a smaller I value. So made of a different material, apparently. And it is moving 8 radians per second, but in the clockwise direction, which they're counting as negative in this case. So what I want you to predict is, based on what you know so far, when the blue one falls and they stick together, will they end up, and don't say it out loud, but think about it for a second, will they end up rotating the same direction that the blue one was going originally? Or will they end up rotating the same direction that the orange one was going originally? What do you think? So in the Zoom, put it in the chat. Will they end up going blue direction or orange direction? And here, just think about it silently for a few seconds, and then we'll have some of you share your thoughts. When the blue one falls and they stick together, which direction will they end up going? Same direction as the blue one or same direction as the orange one? We're getting pretty consistent votes for blue here. Anybody saying blue or orange in here? How many say blue in here? Everybody, okay. All right, so I'm not pulling anything by you guys. Evan, I think you were the first one that I saw put an answer in there. Why did you pick blue? Favorite color?
No, because I was multiplying them together, the inertia and the velocity, to get the momentum. And I guess I thought that since it was bigger with the blue, then it would stop it.
Yeah, that seems logical. Let's see if that plays out mathematically, if it makes sense. And I think you're going to find out it does. So because we know momentum is conserved, we know that whatever the momentum of those two things is in the beginning, it will have the same momentum. And here they've given you the answer. They are going to end up spinning the same direction that the blue one was originally. So our momentum before and after is the same. And just like we talked about with energy, total energy is conserved, not necessarily kinetic, but total energy is conserved. And so that is also true here. Momentum is conserved. And because momentum is conserved, whatever the momentum is before, it has to be the same as it was after. So if we think about the two values, momentum for both would be I omega because they're both rotating. And so we have to think about the rotational inertia and the rotational speed. Afterwards, they stick together. So we could write that side as I1 plus I2 because they still have their own I values, but they have the same omega because they're stuck together. They would be rotating at the same angular speed. Then if we just start plugging the numbers in, as Evan was saying, well, he was thinking I got to multiply those two to get the momentum. So 2 times 5 gives us 10. 1 times -8 gives us -8. And then on the other side of the equation, we just add the 2 and the 1 for the I values, and the omega is what we're looking for. That's what we don't know. We want to prove mathematically why they go in the same direction as the blue one. So if we look at the 10 minus the 8, the difference in those is a +2. And then if we divide both sides by the 3 kg/m² inertia, we're going to get an angular velocity that is 0.667, and it's a positive number. Since it's a positive number, it's going to go in the same direction as the one we defined as positive before. So like we said, it's going to have a like Evan predicted, and I think it sounds like all of you are predicting the same thing. In the end, they're all going to have that same 0.667 counterclockwise angular velocity. Questions on that one? So this is, the question earlier, how do we use it? Like how is it helpful? Because we know it's conserved, it gives us an ability to think about, oh, before and after, I know this before, I know this after, and then I can find missing pieces. Like, well, what is the velocity afterwards? Or maybe there's a collision and I know the velocity afterwards, like this is a collision type. Maybe I want to find, well, what was the original velocity? How fast was that one going? So we can use this knowledge of conservation to solve problems. All right, example 3. Okay, we'll level up just a little bit here. So we got a toy car and a turntable. They are stationary. The car then moves in a circle at a speed of 5 meters per second relative to the ground. So if it wasn't on the turntable, it would be going 5 meters per second straight. But it is on the turntable. So as it starts to go, the turntable is going to start to spin underneath it, and that's going to cause it to go in a circle as well. Now, they're telling us a few things here. They're saying that the disc that this turntable is made of is 16 kg/m², and the car's mass is 1 kilogram. It's just a little toy car. The car is located 8 meters from the center of this disc, and the disc itself has a radius of 10 meters. So if we think about angular momentum, a few things we can figure out. When the car quits being stationary and the disc quits being stationary, when the car starts to move, they're going to spin, and they're going to spin in opposite directions, right? The car's going to be driving one direction, it's going to cause the disc to rotate the other direction. We also know that the momentum before and after has to be the same because it's conserved. And we also know that that just means the I times the omega for each object. We can add them together at the beginning, we can add them together at the end, and the sum has to be the same. So, Sally, because the toy car and turntable are stationary, what do we know about the momentum before?
Well, if it's stationary, it doesn't have any.
Correct.
No
velocity, no momentum, right? So initially, there is no momentum. That means the momenta of the two in the end have to cancel each other. Yeah. Now, they don't have to be equal in terms of each individual value. They may be going at different speeds, but their momentum have to cancel each other out. They have to be equal and opposite, but their velocities don't have to be. All right. So if we start to break down this problem a little bit, we don't know the omega for the car, right? We only know the velocity, 5 meters per second. But we've got this relationship of angular to linear that we've been coming back to frequently. And like I said, these are so helpful and so powerful, and they're not on the AP list, but we keep using them over and over again. We know it's 5 meters per second. We know it's 8 meters from the center of the circle, so we can find the omega, right? So that's what they're showing you here. We plug the 5 meters per second in for V, we plug the 8 meters in for the radius, and we can know that that 5 meters per second linear motion translates to 0.625 radians per second in rotational velocity. Now so that's Sally told us, okay, this is 0, this is 0. The eye of the disk we know. The angular velocity of the disk is what we're trying to find. That's the missing piece. So now we know the omega of the car, 0.625 radians per second. We need to get the eye of the car. Now, they are not giving you an I value, and they're not giving you an equation. So if they don't give you a value and they don't give you an equation, we have to assume that we should treat this as a particle. Okay, we're just treating it as a particle. What is the I equation for a particle?
MR squared.
MR squared. So to find the I value for the car, we just take its mass of 1 kilogram, which was given, times its radius from the center squared, so 8 squared. So the I value for the car is 64 kilogram meters squared. So by using this relationship of how we connect angular and linear values, we get the angular velocity. By using the MR squared, we get the I value for the car as well. Now we know everything except for omega of the disk, because the initial momenta for the disk and the car are both going to be 0 because they weren't moving. And now we know the I and the omega for the car, and we know the I for the disk. So we only have one missing variable. We just go step by step through the algebra. And the angular velocity is negative 2.5 radians per second. And that makes sense. The car was positive 6.625. So the turntable must be in the other direction. We did get a negative answer. So kind of supports that we're on the right track. Questions? Another very AP-ish kind of question. All right, one more. We're going to finish up with one more question about angular momentum. And this is the trippiest of them. Final one, say the best for last. So here you can see the title, an object moving in a straight line can have angular momentum. And I mentioned that at the beginning of the class. We're going to try to show why that's true. So what we're seeing here, it says in the top left, everything here happens on the surface of a frictionless tabletop. So it's like we're above looking down. Okay, they're all laying on a table and we're above it looking down on it. Okay, and this bat has some kind of a pin or a bolt or something through one end of it that's fixed to the table. So that end where the little yellow circle is, that can't move. It's fixed to the table. But the table itself is frictionless. We're in this magical world where there's no friction. And then we've got, it's just sitting there. But we've got this ball that is moving along, and it's made of some clay or Play-Doh or something. And when it hits the bat, it sticks to it. And then they both start to rotate because the ball's stuck to it. Now, here's the question. Before the collision, nothing was rotating. The bat was still, and the ball was moving in a straight line. So it would seem that the system has no angular momentum. How do we know that can't be true?
It's moving.
It's spinning.
It's spinning now, so it has angular momentum now, but how do we know that it can't be true that it had no angular momentum before?
Because angular momentum is conserved.
Angular momentum is conserved unless we provide some external torque, which we aren't. It's just these two things. The system is the ball and the bat. So we haven't done anything extra. Unless we provide some external torque, momentum has to be conserved, and we didn't provide anything else. So the angular momentum we have right now, which clearly exists because it's moving in a circle, has to be equal to the angular momentum it had prior. Yeah.
Well, could it be like it had linear momentum prior and converted to angular momentum?
Linear momentum and angular momentum, because they have different units, we can't add them together. And so it's a little different from energy, where we could say, well, it was potential and now it became kinetic. But those both had joules for their units. And so we can talk about it converting that way. This ball, we know it had linear momentum because it was moving in a line. But that would only translate to other linear momentum. It wouldn't translate to anything angular in and of itself.
Could the linear momentum have been like overpowering the angular momentum before?
You could think of it that way. But the surprising thing is that while the ball is moving straight and it clearly has linear momentum, it somehow also just possesses angular momentum because it has the ability to cause rotation in something else within the system.
It's like potential angular.
It's almost like it's potential, right? But it's actually somehow possessed in the object's movement, that even though it's moving in a straight line, because we know angular momentum has to be conserved, we don't see it. So in a sense, like Nat was saying, it's almost like it's hidden. It's like behind the fact that it's moving linearly, but it actually does exist. It's actually there. Otherwise, it couldn't cause angular momentum to suddenly appear. Angular momentum can't come out of nowhere. It's conserved. So if it has it in the end, the ball somehow had to possess it in the beginning. And so we can use that reality, and we're not going to go through the proof of it today, but you can actually go through and conceptually and mathematically come up with the equation that proves that objects moving in a straight line do possess angular momentum. And we don't have the time to go through that proof today, but what they're showing you here at the bottom is the only thing moving before the collision was the ball. And so if angular momentum is conserved, that ball had to have angular momentum as well as its linear momentum. And there is a formula. Like I said, we don't have the time today. Often we go through, we derive the equations, and we will be deriving a lot of the other momentum equations and other energy equations in the next unit. But for this one, we just don't have the time to go through it today. It's a little bit longer of a derivative, or not a derivative, but how to derive it. And so we're going to just look at what it is. You can see some connections, so you might get some intuition. Angular momentum is I times omega, and I has to do with inertia, so does mass. And we also know that rotational velocity and linear velocity are connected by radius. And so while initially there's no radius of movement within the system, the only radius that this could create in terms of movement is however far it is from the axis of rotation. So they've used D instead of R here, but it's referring to like that R value. How far is it from that axis of rotation? And so there is angular momentum possessed in this ball because it can create angular momentum of the entire system once they collide. All right, so we're going to move on from there and use this m times v times d. This is the third equation. So this is one that is not on the AP formula list as well. Now I will say, this equation, you can solve this kind of a question other ways. And I think that's why they don't give you this equation. But if you know this equation, it makes it way easier to solve. All right, so this is one that they don't give you, but that I do recommend that you put down and keep in the back of your mind. An object moving in a straight line does have angular momentum, and we can calculate it by taking its mass times its velocity times however far it is in a straight line from the axis of rotation when there's the collision, when it meets the other part of the system. All right, so let's go back to the scenario. We got the ball moving along, hits the bat, sticks to the bat. They both start to rotate. So because angular momentum has to be conserved, our before and after picture still should apply. But our before picture looks a little different than it used to, because before the ball had angular momentum, even though it didn't appear to be moving in an angular manner. And so we use m times v times d for calculating how much angular momentum it possessed, even though it was moving in a linear manner. For the bat, we can just go ahead and use I omega because it's not moving at the beginning, but whenever it does move, it only moves rotationally. So we just put I omega for that. And then afterwards, the ball is now moving in angular fashion. So it does have an I value now, and it will have an angular speed, but it'll be the same as the bat. And then the bat has its own I value, and it will also have an angular speed, but it will be the same as the ball. So they'll have the same omega. So if we start to simplify a few things there, one, we know the bat was still at the beginning, so its angular momentum at the beginning is 0. And the ball can be considered a tiny object, so we use mr squared for its I value. And the bat can be considered like a thin rod, so it's going to have a 1/3 ml squared value. Now, you'll notice down here at the bottom, they say the rod is when it's pivoting around its end, the equation is 1/3 ml squared. And then when they put it into the equation, they say 1/3 ma squared. I don't really know for sure why they're changing the variable. There's not really much need to. It makes a little more sense on the next row, but I just want you to see that it's the same thing. What they're calling A is really L. If you look up at the picture, they've suddenly started to call it A instead of D. It's like, I don't know why they're using different letters to represent it in different scenarios. Not really sure the rationale behind that. But whether they call it D, or whether they call it L, or whether they call it R, or whether they call it A or Q, or whatever they want to call it, they're referring to that same distance. All right. What they are going to show here in this next step is they actually now are going to change the R to an A as well and change the D to an A so that they all are the same variable. I don't know why they didn't just start with the same variable, but that's a little confusing in the way they've written it. But now that they've shown, well, that D value was what we're now calling A, and that R value was what we're now calling A, and what we also called L. So let's just call them all A. A little confusing that way, but it does work. It's just variables can be whatever we want them to be. In every case, it's representing the same thing. So now they can just divide both sides by A, and on the left, the A's cancel, and on the right, they simplify. And the A is the same length for every scenario, so they can factor that out. And on the right side of the equation, the omega is the same for the bat and the ball because they're connected, so we can factor that out. And the question wants us to figure out the omega for the bat and the ball, so we just need to take some algebra and move that m of the ball plus 1/3 m of the bat to the other side of the equation and move the A to the other side of the equation. And we have an equation now that we could use to find the angular velocity of the bat and the ball after they collide. Yeah, Ethan?
So if I had something like this situation, like I had my frictionless table and the bat, and I took the bat off and the ball is rolling, it has no angular momentum at the moment. But then if I put the bat on the table, does it like just gain angular momentum from me putting a bat on the table?
No, it has angular momentum in its nature of movement. It's just, we wouldn't need to worry about it unless there's another part of the system that has the capacity to rotate.
Okay.
So it's not that it doesn't exist, it's just that we don't need to worry about it unless it's going to cause rotation. So the bat and the ball both possess both, but the bat never moves linearly, so we don't need to worry about its linear momentum.
Oh, so it's just zero.
Right, yeah. But the ball has both because part of the time it's moving linearly and part of the time it's moving rotationally, so we have to consider both.
Okay.
Yeah. So it's not that it's not there and then suddenly is there, it's always there. Some problems it doesn't matter because it never rotates, so we don't need to worry about it. All right, any other questions on this one? Another very AP type question. Often with this kind of question, you can also solve it with energy. And so we'll come back to another one like this later and solve it with energy, not today, but another day in the next couple of weeks. Yeah, Ethan?
What about the linear momentum? Is that still there? It's just at the edge of the circle, so it's the circumference. Okay.
Mm-hmm. All right, so that is all we're going to cover today for angular momentum. What I want to do to wrap up is to have you practice a problem with torque. All right, and we're just, like I said, we're just going to keep teaching you a couple new things, going back and reviewing, teaching you a couple new things, go back and reviewing. And torque is so frequently used on questions on the AP exam. It's also one that has so many different kinds of problems. I want to make sure we continue to practice. We'll do torque problems probably a couple every week, even though we're not really focusing on torque anymore after this week. We'll keep practicing because it's such a pivotal concept. We'll also come back to rotational inertia occasionally. We'll come back to angular momentum occasionally as well, because we just need to keep reviewing them. For today, I want to spend some time reviewing a problem, and it is about torque. So here is the problem. And to help you understand what's going on here, let's read it together, and then let me give you a little bit more background here. So it says we've got a meter stick pinned to the table, kind of like that bat was pinned to the table in the previous problem we just looked at. And it's pinned to the table as shown. So again, we're looking at it from the top down. okay? So it's not hanging on a wall, it's on a table. So we're looking at it from the top down. And it's got this pin. That pin is where the axis of rotation is going to be, just like there was a pin in the back. Now, two forces are applied to this meter stick such that it does not rotate. Okay. Part A, where along the meter stick is F2 applied? So they're showing you that this force of 4 newtons is applied at 1 meter from the axis of rotation. It's at the end of the meter stick, so it's a meter away. But this one is a 6 Newton force at a 60-degree angle. And they're saying, well, where would that have to be so that the meter stick doesn't rotate? That's the question. Now, part B says, what is the magnitude and direction of the normal force exerted by the pin on the meter stick? So you guys can feel this a little bit if you want. I have some rulers over here. And if you want to grab a ruler to experience it yourself.
Oh, yes, I would love to experience it.
So here's how you can feel this actually. And when you're done with these, just keep them at your table and we'll just wipe them off when we wipe off our tables. So if you want to feel this, you can come get one of those rulers, but the rulers have a nice little hole in it. Okay, and so that's where we're going to pin it to the table. Now, we're not literally going to pin it to the table permanently. You don't damage the table. But if you just take the tip of your pen, hopefully closed so we don't write on the table either, and you just put it in the hole, that's like the pin. All right? And hold the pin up near the top and just push kind of gently down. Now, in this scenario, and if at home, if you want to grab a ruler real quick, you can do the same thing. Even if it doesn't have a hole in it, you can use your thumb and just hold down one end of the ruler. All right, so that's a different experiment. All right, so now what I want you to do is put your fingers in 2 different positions. Put one on the end of the ruler and put one somewhere not on the end of the ruler and push with both fingers. And you should feel it trying to make, like push against each other. Because these are going in the opposite directions. So with your finger on the end, push one direction, and with your thumb, push the other direction. And you should feel it trying to move the pen or pencil, right? As you're pushing, you should feel it trying to move the pen.
Yeah.
So if that's literally pinned to the table, then that means there's a normal force between the pin and the ruler. Is that making sense? It's not normal force like we usually think of it, like a table holding something up. In this case, it's sideways, but it's the pin not letting the ruler rotate when it's trying to. So you can see if I don't hold it strong enough, it makes the pin move. Okay, so that in part B, it's saying what is the magnitude and direction of the normal force that doesn't let the ruler move there, that this pin is providing so that that won't move. That's what part B is asking about. All right, so what I want to do is I want to give you about 5 minutes. And I want to see how far you can get in this question on your own. Okay, so just on your own paper, see if you can at least get part A done and maybe get started on part B. If you get stuck, it's only going to be 5 minutes. I don't want you to be stuck too long, okay? If you want to have some conversations with each other, you're welcome to. Because it's such a short period of time, I don't think I'll put you guys into a breakout room for now. But just for a few minutes, just see if you can get this problem started and then we'll finish it together.
I have a feeling I know what to do.
I probably should have done before, but I wanted to
See what the experiment.
Yeah, that's fine. Thank you. Sure. I know you may or may not be entirely done, but I'm hoping you've at least come up with maybe some strategies to start or at least think about. If you're stuck, that's okay. We're going to figure it out together. I'm going to ask a few of you what ideas you have. If you have an idea, just share it, no matter how far along we were able to move. If you couldn't, if you just felt stuck and weren't sure where to start, that's okay too. But I just want to hear back from some of you on where you're at and what you were able to think about if you were able to think about some strategies. So let's start with Rocky. Did you have anything that came to mind for you on how you could at least start this problem? We're focusing mainly on A right now, I guess.
Well, I tried to find the torque for like the angled one. So I did like sine 60 times 6.
Okay.
I don't know if that's on the right track, but then I did sine 60 times 6, which I got 5.196, and then I divided 4, which is the torque for the other one, I'm pretty sure. I did 4 divided by that number to get 0.77 meters to like for that's where it would be placed.
Okay. Yeah, sounds like you were exactly on the right track. So what made you pursue torque? Like what's the connection? What about the question helped you know to think about torque? And it sounds like you put them equal to each other.
Hold on, let me read the question again really quick, because it's in place, right? It's not rotating, so that's why I was kind of thinking like they had to be equal to each other.
Yeah.
And then the reason I used torque was just because I saw like the force and I saw a theta, so I figured that's the only equation with force and theta in it.
Good. So that's an excellent solution. I'm going to actually follow your lead and show it solved that way. But I want to make a comment on why torque is the best approach for this one. There's 2 forces that we know about, right? But for those of you that tried it, when you put the pin in there and tried to hold the ruler, there were also forces on that pin. So if we want to solve this focusing on forces, we also have to include the forces of the pin here, and we don't really know any of them. So while we are going to think about them, and we are going to need to do that for part B, starting there isn't going to get you very far. It's okay to start there. You just won't be able to get very far. But torque, because these 2 forces are trying to make the meter stick rotate, torque actually works. So and we can get pretty far because we know enough about it. So one way to just show it fleshed out the way Rocky described it is I know the torque of that downward force, the torque that's created by that downward angled force, has to be balanced by the torque of that the torque created by that upward force. If they weren't balanced, it would rotate. And it says it does not rotate. Okay, so if it does not rotate, the torque has to be balanced. And she also talked about the formula for torque. So I know it's F, and so the downward one is 2 times R2, which we don't know, times the sine of theta. And then for the upward one, it's F1 times R1 times the sine of theta. If we just think about the whole equation. But if we start plugging in numbers, we're going to recognize that it actually simplifies down a fair bit from that. F2 is 6 newtons. And R2 we don't know, but we do know the angle. So sine of 60. You just have to make sure your calculator's in degrees if you're going to use 60.
Didn't do
Yeah, if you have it in radians, you don't get the right answer. So if you're going to use degrees, you got to make sure your calculator is set to degrees. If you're going to use radians, you got to change 60 to radians. And then the other force is 4 newtons. And it's at the end of the meter stick, so it's 1 meter. And it is the sine of 90, which is 1. So over here, that all simplifies, like she said, down to 4 Newton meters. And over here, what did you say it was when you took sine of 60 times 6?
5.196.
3 rad 3 if you want to wait to do decimals.
All right, and that would be newtons times that radius. Yeah, so you could use it in radians if you want to, or just use it even in a non-simplified value instead of a decimal value. And then for R2, you said you got 0.770?
Yeah.
All right. And if we're taking Newton meters divided by newtons, the newtons cancel, and we're left with meters. Questions? How many of you got that? You? How about on the Zoom? You? Okay.
I got close, but like I didn't like fully do it. Like I was on the right track. I just didn't get there.
Good, good. Yeah, that's why I want to keep practicing these, because a big part of the issue for these questions is where do I start? And the more problems you see, the more comfortable you're going to be with, well, let me just start here. And that's almost like a paralyzing fear some students have is, what if I start it wrong? And sometimes you just have to start. You just have to get the ball rolling, and maybe you're wrong and you'll figure it out and you'll then restart it. But you know, think about it for a little bit, but don't let yourself get paralyzed if you get stuck. So I'm glad, Aiden, that you had a train of thought and you were on that train chugging down the tracks and you were getting there. So that's good. All right, now part B is the trickier part. What is the magnitude and direction of the normal force exerted by the pin on the meter? So on the meter stick. So these forces are pushing and pulling the meter stick, and the pin is making sure it doesn't go anywhere. The pin is actually giving a normal force. And if you tried it, you felt that the pin wants to move. So there is obviously a force the pin has to supply so that it doesn't. What we need to figure out is what are the directions of those forces, and so we can calculate them. So any ideas on how we can start? Yeah, Ethan?
You can do it almost the same as the first problem. You can set it up as a torque equation. So the F2 is your pivot point, and F1 and the normal force are going to be 2 different forces that are going to become torques. And so to balance it on the pivot point of F2, you know that the normal force is going to have to go up. And then you can set the torque created by that normal force equal to the torque of F1 around the pivot point of
F2. If we wanted to analyze the torque that is there, that could work. But since they want normal force, the normal force won't just be up in this case.
Oh, okay.
Yeah. The other ideas? This is a tricky one. Anybody in the Zoom either, just unmute and say it if you got an idea. You got another idea?
Yeah.
Okay.
Would it be up and left to balance the right part of the force 2.
Okay, now we're starting to come up with some ideas. So this angled force has components, right? Some of that force is downward, and some of that force is to the right. So let's talk about the one to the right first, okay? Because there's only one horizontal force, right? This one doesn't have any horizontal, it's just vertical. But this one has horizontal. So there's only one force that's got, and one component that's horizontal. So if we can figure out what this is, then that pin has to resist it, right? If this force is pushing the meter stick that way, then the pin has to fight that. That making sense? And how can we find this value?
6 newtons times cosine of 60 degrees.
Yeah, the sine, oh, sorry, no, we don't sine for that one. In the last class, we started with the vertical. So if we take cosine of 60, then we get the adjacent. So let's just call this x. We get the x over the hypotenuse, which is 6. So to find that x, you just take 6 times cosine of 60. Anybody have a number?
It's 3 newtons.
3 newtons. So it has a component that way of 3 newtons. But it also has a vertical component. I can use sine to find the vertical component. Anybody find that vertical part?
It's the 5.196.
All right, we'll just go 5.20 for now, just round that off. Now, do we need, does that mean it's going to be battling that 5.2 newtons? Not quite. What does it have to fight? Vertically speaking. So we've already said it has to support that or fight against that 3 newtons horizontally, but vertically there's 2 forces here. There's a 5.2 down, right? And there's a 4 up. So what's the net vertical force?
-1.2 newtons.
1.2 newtons down. Right? There's 5.2 pushing down, 4 up. So the net vertically is 1.2 down. So if the net vertically is down, the pin has to push up to fight it, right? So 1.2 newtons up. What's the resultant? Which way is the, would I draw my resultant vector? Yeah, it's got to go this way and that way, right? So it's got to be like some angle that way to account for both of those, right? Well, remember when we have vectors, we can draw them tip to tail. So to make the situation a little better, I'm just going to slide this over. So I've got this one, I'm going to slide that over so they're tip to tail. 1.2, 3.0. How do I find that?
You square both and then you take the square.
Pythagorean theorem. Anybody have a chance to do that?
Let me just do it mentally real quick.
2.4. Wait, no. 3 squared is just 9. So
3.2.
Yeah.
So now we know the amount of the force. What's the magnitude? We know that. 3.23 newtons. How do we find that direction, that angle?
Trace or inverse.
Inverse.
Yeah.
Take the
Yep.
inverse 10.
The tangent of that angle would just be opposite over adjacent. So if I just use inverse tangent, yeah. You may have that.
21.8.
And that would be 21.8 degrees up and to the left.
Yeah.
All right. So we're out of time, but hopefully that makes sense. Again, combination FRQ question. We've got forces, we've got trig, we've got torque, we've got all kinds of stuff integrated here. For those of you guys that are in the Zoom, if you have any questions for me, stick around, and as soon as we get things wiped down here, I'll be glad to chat with you. If you don't, then enjoy the rest of your week, and I'll see you next week.
Thank you.
Thank you.
You're welcome.
Next week, and the week after that, we got Friday off.
Oh, that's right.
We start break.
You got two full, yeah, Good Friday. Oh, yeah. So you got 2 full weeks coming up and then another short one, right? So many short weeks in this span.
So nice.
When you wipe off your table, if you did use one of those rulers, just use this paper towel to wipe off the ruler as well before you put it away. Appreciate it.
I haven't checked the schedule for whenever we go back from spring break yet, but I think it's not as amazing, but I think we still got to do the walk.
Oh, after spring break.
Yeah. Yeah.
But before that, we have finals and AP tests.
Yes, can't wait for that.
The most comfortable.
Thank you.
You're welcome. Have a great day.
You too.
Thank you. See you. There you go.
Thank you. That door open on the way out, guys. Please, you're welcome. You too.
Thank you, Mr. Webb.
You're welcome. Have a great day.
See you Monday.
All right. So now have you been able to make some progress on the positive physics stuff?
Oh, yeah.
Okay, good. I think was the last one wasn't finished last time I checked. So when you, the chapter 10 one?
Yeah.
So when you're done, just make sure you shoot me an email so I know to go on and check that out first. Okay. Yeah, perfect. Have a great day.
Thank you, you too.